Okay. Right, so last time we looked at the Chapman-Kolmogorov equation. And if you remember, it breaks up a long-term evolution into two short-term evolutions. Right? So what this says, there are different ways to express this. Probability that after n plus r steps, you go from I to j is equal to probability n k xm is I. You land at k after n steps, and then from k you land at j in r steps, and then sum over all k. So alternatively, you can write this in terms of transition matrices from m to m plus r in terms of a matrix multiplication. This is equal to n step times r step. So this matrix multiplication can be written explicitly term by term, that is, as wij so ijth term of this matrix is ij from here I to k m plus n k to j m plus n. So these are different ways of saying the same thing. So the proof is pretty straightforward. Uses our workhorses, theorem of total probability, definition of conditional probability, and then we will bring in the Markov property. So if I look at this form, the ijth element over n plus r steps, this is by definition that I am at j at this timestamp. So p of m plus n plus r, probability of that, given that at m, given at I. That is the definition of that transition. So use theorem of total probability by conditioning it on the state space at k. Right? So bring in the partition here, condition it on the state space at k. Add that intermediate time step. So that, and that after n steps you landed at k, given the same information. Okay. So that's theorem of total probability. And then use the definition of conditional probability to push this information over here, right? And x m is I times x m plus n is equal to k, given x m is I. Right? So we have derived almost this form, right? The only thing that is missing is that this should not be here, and it won't be here if the chain is Markov. Sorry, which one should not be there? This one should not be there. This is the older piece of information. Because given the more recent information, I don't need that because of the Markov property, which is a statement of conditional independence of old information given more recent information. Right? So Markov property is equal to J given that x m plus n is k and you're done. So this is what the Chapman-Kolmogorov equation would look like if your chain was not Markov. Okay. So an extension of this, or if you want to look at R-step transitions, so what we're going to do is we're going to set in the CKE, set R is equal to 1, 2, and so on. So I'm going to look at this form. Okay, bring that in here. For R is equal to 1, this is equal to, that's the n step times m plus n plus n plus 1. But this is from time homogeneity, that's just W, just a single step transition. Right? So that's Wm n plus n times W. So call that equation 1. Now let R be equal to 2. So I'm going to again do a recursion. So that I have for this matrix just a single step. So use equation 1 there, m plus n times W squared. You get a W from here, and this is also a W. And so you can keep that going. And for a generic R, we have that m to n plus n plus r is equal to times W to the R. And set n is equal to 0. So what is Wm comma m? Remember the definition of a transition matrix. M comma n in general is probability that, well, ijth element of that matrix would be that. So from m time, this is the older time step, this is the newer time step. That's what that is, right? So what would it be when m is equal to n? That matrix would look like what? The identity matrix. Right? So WMM, ijth element, would would be the probability that xm is equal to j given that xm is equal to I. This is equal to 1 or 0, right? And it's equal to 1 when I is equal to j, because it's the same term. So when you set n is equal to 0, this becomes the identity. And you get that the R step transition matrix is W to the R. This is not really such a big eye-opener. We already saw this when we were deriving K-step transition the previous lecture. Given the initial PMF, what's the PMF at a later target, right? We got this. So you get the same result from the Chapman-Kolmogorov equation, given time homogeneity, and it makes sense, right? This is the time homogeneity part, that all these single step transitions are the same W. Okay, so since our chain is time homogeneous, it doesn't really make sense to have two indices here, right? So just like we had for LSI systems, we had a single parameter autocorrelation function. It just makes sense to prescribe how many steps were involved, right? So this is the notation we are going to use. WR. This would be W to the R, where W is a single step transition, and WIJ R, here's some notation. Ijth element of WR is by definition the R step transition. M plus R is equal to J, given that X at M given I. Okay, for some M, all M. Okay, so I have an example, a short example. Can you check if the camera is recording? I've had this happen in the past. I record the whole session and go back home and there's nothing. A virus exists in n strains. Okay. And in any given generation, the probability of staying in the same strain is 1 minus alpha, and the probability that change the strain or mutate is alpha, obviously, but then it can mutate to any one of the n minus 1 remaining strains. So this would be alpha over n minus 1. The probability of mutating to the jth strain, where j is not equal to I. And those are the probabilities in a given generation. So there are two kinds of Markov chains you can build here, right? You can have two states, which would be like an abstract state, same, and mutate, or mutate and not mutate. So the probability no. Okay, so let's build the other chain first. So you have strains 1 to n, S1 and S2, Sn. Right. So the transition map and so on from the other strains as well. All of these probabilities of staying within the same strain would be 1 minus alpha, and each of these arcs would be alpha over n minus 1. Right? 1 minus alpha. So you could collect, potentially for each of these strains, you could collect all the other strains into a complement set, right? And have a two-state Markov chain as well. S or S complement, right? Some strain S and S complement. So this arc is the probability of mutation, right? That would be alpha. And I have to think about that a little bit. That'd be the same. So think about that. You can build that without much trouble, right? Just look at the individual, because they are all independent strains. So you can add up the probabilities and come up with these transition probabilities. In any case, so you have, for this Markov chain, W is the diagonal elements are 1 minus alpha, n of them, and all the others are alpha over n minus 1. So the first question is, what is the probability that after k steps you are in strain I, given that at the initial time step you are in strain J? So this is trivial, it's just a direct application of the formula. You're given a one-step transition, you're required to find the k-step transition, right? So you multiply that k times with itself, and this would end up being W Ji K. And this would be the same as the ijth element of W to the K raised to the power K. And I'm being a little loose with the notation. So follow what I'm saying here. This square bracket is the ijth element of this matrix, W raised to the K matrix. Right? This is not equal to 1 minus alpha to the K. Right? I hope that is clear. Because you can come back, you can mutate and then come back. What that is that you do not mutate in each of the K steps. Right? This would be the probability that x0 is equal to j, x1 is equal to j, xk is equal to j. That is different. Another question can be, what is the probability that x0 is equal to xk? I'm sorry, xk. It doesn't care what strain you're in, so long as you're the same strain at those two time instances. Right? So again, you use conditional probability here. Xk is equal to I, given that x0 was equal to I. Sum over R. And it reduces to that same problem. This would be I. Yeah. So this would be W to the K, I, the diagonal element, times lambda naught this is the same as WII So I've messed up over there. Someone tell me something was going on in my head, and I just I was assuming I is equal to j.
Yeah.
Right? That's when I wrote this. Essentially, I'm thinking of I being equal to j. So in the special case that I is equal to j, this is not equal to that. This term is not equal to that, because that would be when you do not change on any of the generations. Okay. So consider a special case that I is equal to j. Okay. So, if you remember, one of the key questions in the theory of Markov chains is, if you're given a Markov chain like that, then the key question is, what is the stationary distribution? Right? And we want to such that pi is equal to pi times w. Pi is the stationary distribution. So when you apply the transition matrix, the PMF does not change. Right? So we want to answer this key question, because in terms of applications, this key question leads to the theory of Markov chain Monte Carlo as well. So in order to get there, we need to build some more theory. So I'm going to spend this lecture and the next one to get there, and then we'll state the main result of stationary distributions. So in order to get there, we need some initial theory. And so we'll begin with classification of the states of a Markov chain. And we've seen some of this when we were doing random walks. So the first definition here is that state J is persistent. You know this. If the probability of returning is 1. So probability that xn is equal to j for some n, given that x naught was equal to j, this probability is equal to 1. Okay. So the state or the chain returns to j, given it started there, sometime in the future with probability 1. And the state J is transient if this same probability at xn is equal to J for some n greater than or equal to 1, even that x naught is equal to J is less than 1. For all right, so this is a classification of this state J, and you can go from one state to the next, and each state may have a different classification, right? Some states may be persistent, and some may be transient in a given Markov chain. So one of the reason we need this is we will see that for stationary distributions to exist, when we are doing existence condition of the stationary distribution, the persistence requirement will be needed. Okay. So an important problem here is the so-called first passage problem. So let Fij be the probability that x1 is not equal to j, x2 is not equal to j, xn minus 1 is not equal to j, but xn is equal to j, given that x naught was equal to I. How is this different from Wij n? This is the n-step transition matrix ijth element, right? So this is the probability that xn is equal to j, given that x0 was equal to I. So these two are fairly different, right? Because we are saying that they do match at xn, but I never visited j from 0 to n minus, from 1 to n minus 1. Right? Here I could have visited j before n as well.
But I mean, because of the time homogeneity thing, if it goes to j, like if it starts from I at x0 and goes to j before n, then can't we do that again somehow? I mean,
yeah, but you will have a shorter time gap between when you first visited j and then the at
that's
n.
true. Yeah.
Right? So this is a very specific way of getting to j,
Right.
without ever visiting it before, because this time step n is fixed. I mean, the time gap from 0 to n is fixed, right? Here, you don't care how you got to j at n. You may have crossed j earlier as well, right? So you expect this probability to be much lower than this. Okay. So this is the problem of first passage. That you first visit j after n time steps. So the first passage happens at n. And so we define Fij as summation Fij n over n as the probability of ever visiting j from I. it's hard to get this probability from W's because it's not a partition. This forms a partition. So you can add this up. Right? You can't add up these probabilities. Okay, so the first thing we'll state as a fact is that J is persistent. Remember, persistence is the property that in return with probability 1. So J is persistent if and only if Fjj is equal to 1. Essentially, those two statements are equivalent to each other. That Fjj is 1 and that J is persistent. Fjj would be probability of ever visiting J from J. The probability is 1 is the same as saying that J is persistent. Call this 1. Alright. So, as we did for random walks, we're going to define some characteristic functions or generating functions. Definition. Define the generating function of. So we have two series here, right? Or sequences. Wij's, the n-step transition, and Fij, which is the sequence of first passage times, right? Probability of first passage happening at n from I to j. So define the generating function of this sequence n from 0 to infinity and Fij as n from 0 to infinity, just the standard way we define generating functions, Fijn s to the n. Now there is a slight problem here because n equal to 0, it doesn't make sense. Right? This is I and j. So we're going to define Fij 0 to be equal to 0 for all I and j. That's a definition. Okay, because when you say so when j is not equal to I, then of course that has to be 0.
Yeah.
Right? And when I is equal to j, then you would think it should be 1. But the way we interpret this first passage when I and j are equal is the probability of first return. Right? So you need at least one time step. So we define this to be 0. Okay? And the generating function of this n-step transition matrix the same way. Wij n s to the n, and this we saw a few moments ago that at 0 this is the identity matrix. So a key term here was the probability of ever visiting J from I. Right? So in terms of these generating functions, Fij, probability of ever visiting J from I, is the sum of these values, Fij n, which is in the S domain, right? Okay. So the first theorem is what we had seen for random walks, so I'm not going to prove it because we proved it there. The proof here is going to be similar, if not identical, to the case of random walks. B, Wij, S. Okay, so we're not going to prove this here because, like I said, we had seen the proof in random walks. Okay. So there are many extensions of this theorem. The first one is the following. State J is persistent so if I evaluate this one, the n-step transition from J to J, is equal to infinity. Okay. Remember what Wjjn is. I'm going to write this on the top so we have that. Wjjn is by definition the probability that xn is equal to j, given that x0 is equal to j. So add up all the n-step probabilities, you should get infinity if j is persistent. I'm sorry. If this sum is infinity, then the state j is persistent. And if this holds, if this is true, then from I to j over n steps, sum over all n must also be infinity for all I not equal to j. So this is a condition for persistence. Take the n-step transitions from j to j, add them all up, that adds up to infinity, then the state j is persistent. that's part A of the corollary. There's a part B as well. That's for the transient part. State J is transient if that sum is less than infinity. And if true, then that sum from some other state I to j, summed over all n, would also be less than infinity for all I to j. Okay, so be very clear about what is being said here. Okay? There are some very subtle differences that we'll see. There are lots of different statements I'm going to make, and by the end of the lecture, might be very confused. So be very clear about what the cause is and what the effect is. So this is the n-step transition matrix. Right? So when you take the transition from j to j over all different number of steps, right? Add up those probabilities that must diverge. If that divergence happens, then the state J is persistent, and if not, that sum does not diverge, then the state J is transient. So the proof is directly comes from that theorem over there on the top. So we're going to have S less than 1. This is the area of convergence inside the radius of convergence of all the involved generating functions there. So from theorem A or theorem 2, WJJS part A is 1 over 1 minus FJJ. Okay, so now we're going to take the limit S increasing to 1. Okay, so limit S increasing to 1, WJJ S, is by definition WJJ S was equal to so this is limit 1. As S increases to 1, this is that sum right. This is from definition of the generating function. From the theorem from theorem 2 part A, we have this limit S increasing to 1 okay. Now this is the condition. Suppose this sum is infinity, right? When would that happen? From here. This implies which is nothing but Fij. I'm going to just keep adding the definitions here to remind you what these are. Fij was Fijn is equal to probability of ever visiting. I made a mistake there, so you're going to tell me what's wrong. J from I. So what's the mistake there? It's JJ. Okay. So this sum being equal to infinity implies that Fjj is equal to 1. And the fact that I had stated was is equal to 1 means that J is persistent. Now I'm a little torn here. I need to go back and look at the text. I haven't done that in the recent past. But just looking at the top of it, seems like this statement should be a if and only if to me. If J is persistent, tell me where the flaw could be, right? If J is persistent, if you assume that now, right? This relationship still holds. This we don't know, right? So we have limit s increasing to 1 is this. Now if J is persistent, then this is equal to 1.
Yeah.
So the sum would diverge. I'm going to go back and check the text. I think that there should be an if and only if.
What about then the line next to it?
And if this is the next one?
Yeah.
Okay, so yeah, that part I haven't looked at yet. Okay, so yes. So if that is true, then from part B, right? Since so what we have is that. So right. So let's look at that. I want to take this out. Over n Wij n. This is equal to limit s increasing to 1. This is from part B of the theorem. Right. Now this is going to increase to infinity because this part is going to infinity, right? As s goes to 1, jj we just saw that. So if jj sum goes to infinity, so this one would go to infinity as well, okay? Because of, like I said, this form. So that should again be true if j is persistent. So I'm going to check on that for next time. Okay, part B. Part B says that jjn less than infinity implies that j is transient. Okay, so again, go through the same list of arguments. We have Wj, J, S increasing to 1. This is of course equal to WJJ n over n. This is from part A of the theorem. Increasing to 1. So it says that this being less than infinity would mean that this is less than infinity, which would mean this is a probability, right, that Fjj is less than 1, which implies that J is transient. So again, this list of facts just as reminders. The fact stated that J is persistent if and only if Fjj is equal to 1. Okay. And again from part B, see that Wij n is less than infinity for all n, for all I. Okay. Okay, before I move on, just a little observation. So let Ni be the number of visits to I for n starting from I. Okay. So after it started from I, how many further times it visited that state? So probability that Ni is equal to infinity, what do you think the probability will be when I is persistent? Is 1 when I is persistent. And the probability that number of visits to I is infinity is 0 when I is transient. Because essentially once you revisit, the chain resets, right, and you start all over again. All right. So the next one is, this was the classification of states. Now we'll do a time classification. So we classified states as persistent or transient. The next one, if you remember, was a classification in terms of mean recurrence times. How much time does it take to come back, right? So that's the time classification. So you have a null or non-null states. So the definition here is, let Tj be minimum of n of all times such that xn is equal to j given xn x0 is equal to r. And again, this is just another way of writing the time of first passage is defined as the time of first passage to J from I. So when we are trying to classify the states on the basis of time, we're going to do that in terms of the expected value of this time. Right? Probability that Tj is equal to infinity, given that x0 was equal to j. Okay, so that Tj is slightly, so this is slightly different here, right? Tj is the minimum time where this chain crosses J starting from I. So this is saying that the chain started from J, right? And the time, the minimum time that the chain returned to J is at infinity. This probability is greater than 0 if and only if J is transient. There's no need for this probability to be 1. Right? There is a chance that this probability may be greater than 0 if J is transient. And then the expected value of Tj, given that x naught is equal to J, is of course equal to infinity, because what was the name that we had given for such PMFs that where the probability of it assuming an infinite value is non-zero? Deficient. Okay? So Tj is deficient. So all this new jargon leads to the concept of mean recurrence time. The next definition. Mu J is the expected time of first return, given that we start from that point. And this is the expectation of Tj and Fjj and sigma. So infinity when J is transient, and this sum when J is persistent. Right? This sum is defined here because Fj, so this is identical as this probability. Right? This is the first recurrence of J, starting from J. Right? So this value when n goes to infinity is 0 for persistent J's. Right? So that expected time is defined. Now that doesn't mean we learned a lesson in random walks, right? This does not mean that this cannot be infinity. That can still be infinity, that summation. We saw that in random walks. that the origin was persistent, meaning that the chain would return to the origin with probability 1, that was when the walk was symmetric, right? Equal probability of taking a step to the left or right, and yet the expected time of that return happening turned out to be infinity. So this can still be infinity, right? But in general it has this expression, it can be less than infinity as well. Okay? So you're just going to state that mu j can be infinity even for persistent j. Okay, so that leads us to the definition that we are after, the classification in terms of time. A persistent state j is null if mu j is equal to infinity, non-null if mu j is less than. This is also called positive recurrent. Okay? Alright, so the theorem here is a persistent state J is null if and only if. So the state J is persistent now, that we know. Now we're saying that it's null if and only if Wjj m goes to 0 as n tends to infinity. And if true, Wij m goes to 0 as n tends to infinity for all I. Okay, so I'm going to draw a big diagram here to kind of summarize all the results that you've stated so far. And it's nice to have this in the backdrop, all these definitions, so you can remember. But these are, I'm just going to add to this Fij n. Was, remember, the probability that x1 is not equal to j, blah blah blah, but xn is equal to j, and that x not is equal to y. Okay, so this is what we have so far. Just I'm going to draw some blocks. J persistent, state J transient, state J being null persistent. So it is persistent, but in addition it's also null. Right? Now, some conditions. Over n is equal to infinity. Wjj n tends to 0. So So first, some sanity checks, just to make sure whether or not we are on the same page, or we are losing our minds here. Does this imply that? So this is the sum of the series. When you add infinite of these terms, is less than infinity, right? So essentially, in some sense, you're thinking, oh, this sequence is dying out, right? As it increases. So does this imply that? No, because you know this sum, right? Right? This is infinity, this summation. But the nth term goes to 0. It's not dying fast enough. So, I'm just going to draw some blocks here, some implications here. Just going to say that. Okay? Just so we know that we're not getting confused as how are these conflicting conditions happening. It's slightly non-intuitive, but that's what it is. Right? But does this imply that? Yes. Oh. Okay. And there is no relationship between these two blocks, right? Like we just saw. Okay, so one thing that we saw is that when this sum is infinity, then we have that implication. And I said that I'm going to go back and check whether this is true or not. Right? The same way, we proved that summation being less than infinity implies this, and I want to check if that's true. Okay? The final theorem here about null persistence says that these are equivalent. Okay? So both of these things are related to persistence. Look. Right? This is telling us that when that sum is infinity, then it is persistent. So if that sum is infinity, can you still be null? Yes, because this can also be true. Because these two blocks are not related to each other. This nth term can die out, right? And you can still have this, and you would be persistent. Okay, so I guess that still does not disprove this part, right? Just trying to think if that's the argument for why this other direction is not true. Right, so this can still be true. Now there's one result that I kind of skipped over in my notes. I'm just going to state this in this big diagram. So this result says that if J is transient, then Wij n goes to 0. So in this diagram, I need another block. So here's the other result that I did not state here. So if J is transient, then the nth term goes to 0. And so, you would still get the same flow here. Because all this is saying is that the state is null. You can forget about the persistent part because the expected recurrence time would still be infinity when you translate. Right? So this flow is okay. Okay, so this is what we have seen. These are all the relationships that we have looked at. The important thing here is that these two are not related, right? And this is a one-directional relationship.
Isn't that forward imply then proven the first one where you have the question mark?
Yeah.
So if it is persistent, then there are only two cases, right? It's either null persistent or it's just persistent. And in both cases, that forward imply holds. So wouldn't that prove that only if, or no?
So it is if and only if.
Yeah, that's what I'm thinking.
Right. So you're saying that it's either null persistent or it is null recurrent. I mean,
Just like
positive recurrent.
Yeah, so yeah.
Right. So, but where is the result about the positive recurrence? That is not here in this diagram.
So if it is persistent, then there are only two possibilities.
Right.
And in both cases, that right side block is true, isn't it? I mean, it is.
Which of these blocks is true?
The topmost one.
No, if this is true, then it has to be null.
I thought it was just persistent if that is true.
Right. So if this is true, then it's persistent.
Yes.
Yes.
But if it is persistent, then in both cases the right hand side is also true.
But if it is persistent, then in both cases, which is true now?
The right hand side, the topmost one. Because that's what I thought we just said.
Right hand side. This.
Yes. The topmost.
Right. So that's what we want to show. We don't know. I think that is the case. That's why I have the question mark there. I'm not sure about that.
Right, so as a proof I'm saying since both null persistent and positive recurrent, it holds, right? That's what we just said. Because we said even in null persistent case, if it goes to 0, the sum can still be infinity.
Right.
So that means both for null persistent and positive recurrent, the sum